So one topic that I really struggled with in organic chemistry was taking a two-dimensional representation of cyclohexane and drawing it in its chair conformations, specifically when it had cis and trans substituents on it. I really wasn't sure if these substituents coming out of the page or the ones going in the page went in the axial or the equatorial position. And so basically, just by looking through the textbook and the notes and looking at a lot of different example problems, I realized that it doesn't matter which one you put in which position, because after you perform the ring flip on the chair conformation, both options are going to be covered. And so one example of that I really want to show you is right here. It is trans 1,3-dimethyl cyclohexane. And so you can see right here we labeled the carbons 1, 2, and 3. And so first we're going to start by drawing one of our chairs. Never was the best at this, but that's okay. And so like we did up here, we're going to label our carbons 1, 2, and 3. And now we need to add our two groups. And we know that this is the trans form. So one of these groups is going to be equatorial and the other is going to be axial. So you say, okay, well, which one is which? Well, let's just start with putting this methyl group on carbon 1 in the equatorial position, which means since it's trans, we will be putting this carbon on the CH3 in the axial position, which is great. And this is where I would really get caught up, was like the arbitrarily deciding which one goes where. But what I figured out was once you perform the ring flip, and we'll draw our next conformation, so after the ring flip, this is still 1, 2, 3. What happens is that hydrogen that was equatorial is now going to be axial, and that one that was axial is now going to be equatorial. And so this is really helpful because now you can see that you have both cases that are trans, and you've put each methyl group in both the axial and the equatorial position. So now, after you do something like that, the important thing to do is figuring out which one is more stable. And how you do that is you look at both of your chair conformations, and you have to see which one has the larger substituents in the equatorial position. Now, that's not really what this example shows. This was more highlighting how to put it in the chair conformation and do the ring flip. But we can do another example where that is possible. So let's say instead of a CH3 group here, let's say this is an iodo group, okay? So then what that does is say we'll make this axial and an axial iodo group, and then so over here it's going to be an equatorial iodo group. So what that does is now we can look and say, okay, the ones with the more equatorial groups are the more stable. So here we have an equatorial CH3, and over here we have an equatorial iodo group. So the iodo group is going to be larger, which means that out of the two chair conformations, this one is going to be the more stable. And if you just look at simple examples like this, it becomes really easy to even do more complicated problems, and then you just start picking it up like with anything else. The more you practice it, the better you're going to get at it. And so yeah, that's how you take care of that. But two other topics that I really struggled with were differentiating between SN1, SN2, E1, and E2 reactions. And I think there are a lot of other videos that really help with that too, especially figuring out like what are good nucleophiles and what are good bases. And I also struggled with chirality, and what was a really good resource for me for that, that's helped a lot, is watching Khan Academy videos. So I hope this was very helpful, and let's hope the rest of the semester goes well for everyone.